Types 3 session is this afternoon, and the aim of this is just to give a quick bit of background information to the 4 talks that are going to be presented in that session, to give people who maybe are not up to date with the latest research some idea of what sort of thing they can expect and what kind of things they might be expected to know to follow the talks. So I mean, this is POPL, lots of talks on type systems, and there are a whole bunch of questions that we ask about type systems. So, you know, mostly things about whether it actually works to provide some guarantee about the runtime behavior, and if we're using it for optimization, is the use that we're making of that correct? And of course, this is POPL, so we expect all these things to come with formal proofs. We're also interested in how expressive a type system is. So what kinds of programs are actually in practice going to be accepted or rejected by the type system, and what kind of properties, what kind of invariants can we express in the type system? And then there are slightly subtler questions that sort of tell you whether the type system is well behaved. So you might ask whether the type system is stable under certain sorts of naive, simple program transformations. So does beta reduction preserve types and that kind of thing? And then there's questions related to more algorithmic concerns. So can we check the types automatically, always or sometimes? And also, can we do it efficiently? Something that I never worried about until I started working on compilers in a commercial environment, and I suddenly realized that I was more interested in performance than I was in anything else. And checking types is sort of the simple side, and inferring types, giving an untyped program and trying to have an algorithm which produces a type for a program. Is also a problem. And finally, is it actually usable? So we care about whether a type system can give good error messages, whether you have to write lengthy annotations on your programs, and very importantly, is the behavior of the type system predictable? Do programmers understand what the type system is doing when it type checks their programs, or what's wrong when it says there's something wrong? So the talks in this session have all got something to do with the algorithmic bit in the middle there. So they're all about inference and checking. We should give some background on the language features that these algorithms deal with. So first language feature is parametric polymorphism. So I guess everybody who's made it to POPL probably has some experience of the Hindley-Milner type system, the ML type system, a very well-known and classic sweet spot in the design of type systems. So it has let polymorphism, which means that polymorphism is only expressed in terms of let-bound variables in the context. They're assigned type schemes, and then those type schemes are instantiated with types which are not themselves involving quantifiers. So this is a predictive system. So there's a distinction between types and type schemes. So inference for this, as everybody knows, is decidable using a unification-based algorithm W. And this also has a really nice property that it yields principal types. So not only does it infer a type for a term, it infers a type which is the most general in this type system. So all others can be obtained from it by substitution. So theoretical complexity of this algorithm is absolutely terrible. Deterministic exponential time complete, I think. But in practice, it works very well. And the expressivity is sufficient for everyday functional programming. So, you know, those of us who use OCaml, it's a bit fancier, but it's basically the ML type system, and we're kind of happy with it on a day-to-day basis. There are some natural, but as soon as you go beyond this, so the extension, for example, with polymorphic recursion has undecidable inference. And by polymorphic recursion, I mean the situation like this type alpha seq, which sort of is a funny representation of balanced trees. So an alpha seq is a nil or a cons, which has an alpha in it, but then it has an alpha seq, which is an alpha cross alpha seq, so that's got sort of twice as many things at the next level down in the tree. And if you write a function like length on here, which is taking advantage of the fact that the lists are of predictable length, then the recursive call to length here involves an instantiation of the type with a different type. So alpha on the outside and alpha cross alpha on the inside. And so OCaml allows you to put an annotation on there, because otherwise you can't generally infer this kind of thing. So then going beyond that, there's the classic Girard-Reynolds polymorphic lambda calculus, or system F. So here, this is first-class polymorphism. Quantified types are types, and you can instantiate type variables with quantified types. So this is known as an impredicative system. And type checking for an implicit version of this is undecidable, as Joe Wells showed back in 1994. So this is good for simple functional programming, but modern languages really want the power of general first-class polymorphism. So languages like Java and C#, they have generics which are at least considerably more powerful, in fact, than this in some ways. But those type systems are undecidable. And indeed, last time I looked, it was quite easy to make the type checkers crash or loop. So what you have to do is balance this expressivity with what you can check or infer. And ways of doing that are you can put arbitrary resource limits on, or you can use some kind of incomplete algorithm. So it's sound. If it types a program, it's OK. But many programs which do type will not be given a type. So you can do that in a hacky way, like just put some resource limits on, or you can try and define a syntactically sort of natural and explainable restriction of the full type system, which does have some kind of decidable inference. So other language features which get covered in this session, apart from parametric polymorphism, are intersections and unions. And if you think of types as sets of values, as you should, then these are very natural things to have. So intersection just means if E has type A and B, then it has type A and it has type B. This is very expressive. It gives you ad hoc polymorphism as opposed to the parametric polymorphism of system F. So you could say plus has type int to int, int cross int to int, and string cross string to string, probably concatenation. But for intersections are very undecidable. So in fact, the first order intersection typable terms are exactly the strongly normalizing ones. So it's kind of obvious that you're not going to be able to infer those in general. Oops. But I'll also, if I go back, and the reason it's very undecidable, I mean, the reason it's very expensive is kind of obvious because you have to type check the same term lots of times to infer intersection types. And union types have similar problems that, if you're eliminating a union, then you have to have multiple derivations for the same term because you have to sort of say, what if it was an A and what if it was a B? These systems also have the disadvantages that types are often very large. Now, this was very unfashionable for a long time. People who designed typed languages from scratch almost never included intersections and unions. But now we're putting types on different things. We're taking untyped languages like JavaScript and PHP, and we're putting types on them. It turns out we really need these in order to type the programs that people have already written in those languages. Other language feature that's important in these talks is subtyping. So again, if you think of types as sets as values, this is pretty obvious. We say A is a subtype of B. Means that the meaning of A is a subset of the meaning of B. Inheritance, as everyone knows, induces subtyping, as do intersections and unions. Implicit parametric polymorphism induces subtyping, where you can say that a polymorphic type is a subtype of its instantiations, and there are rules which are shared between most of these systems, such as the contravariant-covariant rule for function types. So the papers in the session consider these sorts of things. So this one, when subtype constraints liberate, this studies the problem of type inference for an implicit first-class system F-style polymorphism. And it's built on, it uses upper and lower bounds for quantified variables, so in the subtyping sense. The subtyping relation for this is probably undecidable, and hence the inference would be. So what the paper presents is an incomplete but sound inference algorithm for this syntactically restricted system that works only with subtyping constraints and uses a heuristic to ensure termination. One of the things that's sort of interesting about it is that the inference algorithm will infer types inside which the user can't write on the outside. It's as an implementation and a nice comparison. Parametric polymorphism for structural parametric polymorphism. So this is the related problem of subtyping for recursive parameterized types. And this gives a declarative presentation of a decidable fragment of the language, which is based on restricting the subtyping between named types to things which are kind of variance-based. So to rules like this one here, which says if kappa is a subtype of kappa prime, then E of kappa is a subtype of D of kappa primed. This is also interesting because the algorithm works by forward saturation to derive rules like this and then uses those in inference. And this is really nice. This is simple, it's natural, it's powerful. It's something that I think people look at and think, yes, we really should have done this before. It's an excellent paper. Polymorphic type inference for dynamic languages. This is everything. So type inference for ML-style polymorphism with subtyping, intersections, and unions. This is an incredibly rich collection of features which lets you give really precise types to dynamic code, including things that use typecase. And the paper gives a sound, incomplete algorithm that uses backtracking. So this is super powerful. The drawbacks are potentially performance, because it takes a very long time to infer these things, and predictability. But you can give absolutely excellent types to real code. And then finally, this paper, Unboxed Data Constructors, or How CPP Decides the Halting Problem, not like the others at all. It's also about type inference, but it's about a type system which is used for optimization. So when constructors of some type can be represented unboxed, i.e. without tags on. This can lead to significant speedups, but if you want to do this, you have to check that the unboxing annotations you've put on your types are correct. So that means you have to check that the representations you're going to use at runtime don't overlap. That means unfolding the definitions when one type refers to another. And the paper presents an on-the-fly, sounded complete termination detecting algorithm for this kind of unfolding. So novel, well, it seems like a novel algorithm, but then amazingly, it turns out that this is essentially the algorithm which CPP has been using since 1986 to ensure the termination of macro expansion, which is also here shown to be correct. And this is unrelated to the other three, which are all kind of in the same space, but I will say this is neat, it's well written, useful, and entertaining. So it's a very easy read, and I recommend you read it. Okay? Thank you.